We are now going to talk about both the mean value theorem and Rolle's theorem. We'll start with Rolle's theorem. This theorem says, let f be a continuous function on a closed interval. So we have continuous function with two endpoints. This function is differentiable on that interval. If f of a equals f of b, so if the two endpoints have the same y value, then there must be at least one number in that interval such that f prime equals 0. So this theorem is saying if we have two endpoints that have the same y value and we draw a continuous differentiable function, between those two endpoints there has to be a place where we have a horizontal tangent line. And I have an example shown on the screen, but my graph could look differently as well. Any way that I connect two dots such that the endpoints have the same y value, as long as I draw something that's continuous and differentiable, I have to have at least one place where the derivative is 0. Now, the mean value theorem is actually a tilted version of Rolle's theorem. The mean value theorem says let f be a continuous function on a closed interval that's differentiable between those endpoints. So we have a continuous and differentiable function with two endpoints. The difference here is the y values don't have to be the same for the mean value theorem. The mean value theorem says there has to be at least one number c where the derivative is equal to f of b minus f of a divided by b minus a. So what this is saying, this right-hand side, f of b minus f of a over b minus a, that was our average rate of change. That is actually the slope of a line that connects those two endpoints. And the mean value theorem is saying there has to be a place where the derivative, where the instantaneous rate of change, or the slope of the tangent line, is equal to the slope of that secant line. And if you tilt your head or tilt your screen, you should be able to see that this is really similar to Rolle's theorem. It's just tilted. So mean value theorem says if we have a continuous differentiable function, there has to be a place where our instantaneous rate of change is equal to our average rate of change. Here's an example. Verify that f of x equal cosine 2x satisfies the hypotheses of Rolle's theorem on the interval from 0 to pi. Then find all numbers c that satisfy the conclusion of Rolle's theorem. The hypothesis of Rolle's theorem says that our function has to be continuous, differentiable, and the two endpoints have to be the same. Because I'm dealing with a trig function, trig functions are continuous on their domains, and the domain of a cosine of 2x is all real numbers. So this function is continuous for all real numbers. A cosine wave has a derivative that's negative sine. So that means this function is differentiable everywhere. Its derivative is going to exist everywhere. I also just know that cosine waves, they don't have any sharp points on them, so they're differentiable everywhere. And then finally, those endpoints, if I plug 0 into cosine of 2x, I get cosine of 0, which is 1. And if I plug pi in, I get cosine of 2 pi, that is also 1. So my endpoints are equal. So that means Rolle's theorem should work for this function. Rolle's theorem says there has to be a place on that interval where the derivative is 0. So I found the derivative of cosine of 2x using my chain rule. Derivative of my outside function was negative sine of 2x, and then I had to multiply by the derivative of the inside function, which is 2. So negative 2 sine of 2x is the derivative. I'm going to set that equal to 0 and solve. If I divide both sides by negative 2, I get sine of 2x equals 0. And now I have to think about my unit circle. So where on the unit circle does sine equal 0? Sine is the y-coordinate on the unit circle, so it's going to equal 0 at 0, pi, 2 pi, 3 pi, 4 pi, anything that's coterminal with those angles. Now in this case, I don't have sine of x, I have sine of 2x. So that means 2x could equal 0, pi, 2 pi, 3 pi, etc. And if I divide everything by 2, I get x equal 0, pi divided by 2. 2 pi divided by 2 is pi, 3 pi divided by 2, etc. Okay, so which of these values satisfies the conclusion of Rolle's theorem? Rolle's theorem says there has to be a place somewhere between 0 and pi, not including the 0 and pi, but there has to be a value between 0 and pi where the derivative is 0. And we have that. Pi over 2 lies between 0 and pi, and that is a place where my derivative is 0. Let's do something similar, but with the mean value theorem. Verify that the function 1 plus cube root x minus 1 satisfies the hypothesis of the mean value theorem on the interval from 2 to 9. Then find all numbers that satisfy the conclusion of the mean value theorem. This function is continuous everywhere. Radical functions are continuous on their domains, and the domain of a cube root function is all real numbers. So this function is continuous everywhere. Let's see, is it differentiable? Well, we've got the function 1 plus x minus 1 to the 1/3. So to take the derivative, I would bring down the 1/3, and I get x minus 1 to the negative 2/3. And then technically we have to use the chain rule and multiply by 1 because 1 is the derivative of that inside function. I can take that term to the negative 2/3, move it to the bottom. And so now I've got 1 divided by 3, x minus 1 to the 2/3. So this derivative exists everywhere except x equal 1. This derivative is undefined when x equals 1. That means this function is differentiable everywhere except x equal 1. But the interval I care about is from 2 to 9. 1 is not in that interval, so we are safe from 2 to 9, and the mean value theorem should apply. So the mean value theorem says there has to be a place where the derivative, which I already found, it's 1 over 3 x minus 1 to the 2/3. There has to be a place where that derivative equals my average rate of change. I'm going to compute the average rate of change by finding f of 9. So I took 9, I plugged that into my original function, and I got 1 plus cube root of 8, or 3. Then I plugged 2 into my original function. 1 plus cube root of 1 is 2. So average rate of change would be change in y, 3 minus 2, over change in x, 9 minus 2. So average rate of change is 1 divided by 7. So the mean value theorem says there has to be a place on this interval between 2 and 9 where this derivative is equal to 1/7. So I'm going to take my derivative, set it equal to 1/7, and solve. We could cross multiply here, or since both numerators are 1, that means these two denominators have to be equal. So 7 has to equal 3 times x minus 1 to the 2/3. I divided both sides by 3. And then this 2/3 power means I have a cube root and a squared. So my equation is now 7 divided by 3 equals cube root x minus 1 squared. To get rid of the cube root, I'm going to cube both sides. 7/3 cubed is 343 divided by 27. That now equals x minus 1 squared. To get rid of the squared, there we are, to get rid of the squared, we can square root both sides. We technically need a plus or minus, so x minus 1 is plus or minus square root 343 divided by 27. And then I add 1, so x equals plus or minus square root 343 divided by 27. So there are actually two places where the derivative is equal to 1/7. The mean value theorem tells me that at least one of these numbers has to be between 2 and 9. And so I used my calculator, and the one with the plus sign is between 2 and 9. And so the mean value theorem, the number guaranteed by the mean value theorem, is x equal 1 plus square root 343 divided by 27. I have one more example. Let f of x equal x plus 1 divided by x minus 1. Show that there is no value of c on the interval from 0 to 2, such that f of 2 minus f of 0 divided by 2 minus 0 equals f prime of c. Why doesn't this contradict the mean value theorem? Why is this not a problem? So I'm going to start by finding that average rate of change, f of 2 minus f of 0 divided by 2 minus 0. F of 2, if I take 2 and I plug that into my function, I get 1. F of 0, plug 0 into the function, we get negative 1. So my average rate of change would be change in y, so 1 minus negative 1, divided by change in x, 2 minus 0. 2 divided by 2 is 1. So average rate of change from x equals 0 to x equals 2 is 1. And now let's find our derivative. We're going to have to use a quotient rule here. The top is x plus 1, the bottom x minus 1. So both f prime and g prime would be 1. Plugging that into my quotient rule, I get f prime times g minus g prime times f. So 1 times x minus 1 minus 1 times x plus 1 all over g squared, all over x minus 1 squared. We can simplify by distributing and combining like terms. So in the numerator, we've got a 1x minus 1x, that goes away, and then a negative 1 minus 1, that's negative 2. So this derivative simplifies to negative 2 divided by x minus 1 squared. All right, so let's see if we can find a place where this derivative equals my average rate of change. Is there a place where this instantaneous rate of change equals the average rate of change? So I'm going to set my derivative equal to 1. And then I multiplied both sides by x minus 1 squared to turn that into negative 2 equals x minus 1 squared. To solve this, we would take the square root, but we can't take the square root of a negative. We're not going to get a real solution here. And so that's telling me there is no real solution. There is no value of c on that interval where the instantaneous rate of change equals the average rate of change. So why isn't this a problem? Why doesn't this contradict the mean value theorem? Well, the mean value theorem says our function has to be continuous and differentiable to be a place where the instantaneous rate of change equals the average rate of change. And this function is not continuous at x equal 1. The denominator has an x minus 1. Rational functions are only continuous on their domains. And this function is not defined when x equals 1. So this function is not continuous at x equal 1. 1 is in the interval from 0 to 2. So the mean value theorem does not apply to that interval because the function isn't continuous. That was my last example. Please reach out if anything is unclear.